It's my pleasure to introduce Andrew Singletary, the co-founder and CEO of 3 Laws Robotics. 3 Laws is a cutting-edge robotic software company specializing in safety software for autonomous vehicles, aircraft, and mobile robots. Andrew's research has significantly advanced the understanding of how autonomous systems can be made safer and more reliable. He's also earned himself a spot on the Forbes 30 Under 30 list, which probably makes him the youngest person in the room. So with that, I'm going to hand you off to Andrew Singletary to close out this morning's presentation. Andrew, come on up.
Well, thanks everyone. It's an honor to be here. I'm going to be talking today about the trade-offs between speed and safety and how you can best mitigate them and optimize for different use cases. A little bit about myself. I started researching safety critical control back at Georgia Tech. I then went and did my PhD at Caltech. I did this alongside the 2 co-founders of my company, Professor Aaron Ames and Thomas Gurrier, who's here, and you may have met. And the vision was really, how do you actually prove that a control system is going to be safe, prove that it's not going to do anything wrong? So it's been really cool to see this from just something we built in a lab to keep a Segway upright to something that we just flight tested on an F-16, which I'll show a video of today. But we've deployed this software in robotics, automation, aerospace, and marine applications. And the last thing I wanted to say, I'm a member of the A3 committees for R1506, R1508, and ISO TC299. So special thank you to them for putting this on and all they do in the safety community. So the next slide is going to be the agenda, so I can go ahead and start talking about that. I'm going to be talking about how safe autonomy and dynamic safety relate to the overall equipment effectiveness of robotic systems. I'm going to give examples both from AMR as well as from automotive and aerospace. So perfect. Okay, seems like we're good. So like I said, going to be talking about safe autonomy, dynamic safety, and how it all relates back to overall equipment effectiveness and examples from AMRs, autonomous vehicles, and aerospace. So to set up a little bit of the motivation and the problem definition, the real objective is to increase your overall equipment effectiveness. This is a metric out of the manufacturing community that's equal to the availability of a system times the performance of that system times the quality of the output of that system. So we're going to be focusing much more on the first 2, availability and performance. And we really want to look at where you get downtime from availability and performance. So availability is just a measure of how often is the system up relative to how often you'd want it to be up or how often would be ideal. So if it's up 90% of the time, you get a score of 0.9. Performance is a measure of how quickly the system is doing its task relative to how quickly it could be able to do it in an ideal scenario. So some of the losses that typically happen from availability, they're called time losses, and they occur from unplanned or planned stops. Examples of that would be a hardware component failing. It could be a safety system that got to be triggered from a safety incident and the system's down. Performance loss, also known as speed loss, that happens due to much smaller and shorter time losses, as well as just slow cycle times. An example of a small stop would be something like the dynamic environment changed. The robot needs to stop for a second and replan. That's not considered an availability loss. It's considered a performance loss. And so we want to be able to maximize the runtime and the speed. And the problem is that these objectives often conflict. And so that's going to be a recurring principle throughout this presentation, talking about competing objectives and talking about the best way to balance them. Some of the trade-offs you can immediately think of when you think of high speeds, and how they might not always translate to higher ROI, even though you'd think higher speed is always better performance. But you also have to think about things like the power consumption, a faster actuator and brake degradation, things like load shifting that's particularly relevant with things like forklifts. So you don't want to cause an incident or you don't want to cause damage of any goods. And then grid locks are also a big thing to consider in multi-robot environments. So just like humans, when there's a traffic jam, it can be caused by something as simple as one person braking and then that wave propagating. The same thing can happen in multi-robot scenarios. So even though we do want to maximize speed, I want to give a special note that you want to limit rapid accelerations because they're the source of a lot of problems like this. So, not only is speed not always indicative of ROI, but there's also that fundamental trade-off you have to think about when it comes to speed and safety. So there's first kind of just the obvious case, like imagine you're driving a car. The faster you're going, the more dangerous you are. These are some fatality statistics for pedestrian accidents. And so it doesn't just come from the fact that you're moving quicker, you've got more momentum. You also have less time to react to something going on. And the car has more inertia, so it's harder to stop, it's harder to move out of the way. So that's kind of an obvious trade-off between speed and performance, but there's a much deeper, more fundamental trade-off between making a system robust or making the system safe, and making the system performant. And this is a trade-off that's a lot harder to quantify than something just like, the speed of a moving car. And so a lot of the objective of this talk is to really understand this trade-off and learn how to optimize it in different cases. So I want to look at that trade-off that I was talking about between safety and performance. And I think the best way to explain it is to look at the two extremes. So here at the bottom, we have an example of an autonomous forklift. It's going to have uncertainty in its sensing, a potential inability to pick up the human. There's going to be uncertainty in things like braking distance. That's going to depend on how worn the brakes are. It's going to depend on the floor that you're on. And then, of course, there's potential actors in the field. So there could be a human. That human could have a velocity that's hard to estimate. And at any time, that human could change its direction. And so if you really want to be as safe as possible in a scenario like this, you're going to be extremely conservative, and you're going to limit the performance of the vehicle. You're going to have to account for the worst case actions of the human, account for the worst case uncertainty in your sensing. And so obviously that's going to result in low OEE through the low performance metric. On the other hand, if you try to just purely optimize for performance, let's say you consider nominal cases for the sensing, nominal cases and perfect estimation of the human, you're going to get a really fast moving system, but it's probably going to go down a lot because of different issues. So even though your performance might be high, your availability is going to be low. And so both extremes of safety and performance are not ideal when it comes to making an efficient, productive robot. And so we just want to be able to make an intelligent decision on where we are in this space, driven by safety requirements, and be able to kind of optimize the performance from there. The last thing to consider is when you're making this trade-off, there's likely an efficiency gap between the actual true potential of the system and kind of the design space that's available to you. The source of that efficiency gap are things like corner cases that you can't really handle very well, things like uncertainty that's very hard to quantify and propagate through the system. And so it's very important to start looking at this because there's really two objectives when it comes to being able to make a decision about the design of a system. The first objective is to just have the largest design space as possible. So really being able to get as close as possible to the system potential. And then the second objective is to really understand where to fit along that curve. So how much safety do you need? How much performance do you need? Because there absolutely is such a thing as too safe when it comes to mobile robotics. To really frame this in the lens of safe autonomy, I want to talk about how you can achieve high performance and safe autonomy. But I've used the word safe a couple times. I want to make it very clear what I talk about when I talk about safety, because there's two axes of safety that are both very important to think about for autonomous systems. The first is what more people are familiar with, the functional safety side. This is more about how do you mitigate risks from system failures, and how do you mitigate a system failure even happening in the first place. So for example, what do you do when a sensor fails, and how do you design a system to be redundant against sensor failures, possibly by having multiple systems. Safety of the intended functionality, or SOTIF, is another very important concern, especially when it comes to autonomy. So this is all about mitigating risk from what are called functional insufficiencies. So there can be times where everything is working on the robot, there's no system failures whatsoever, but an edge case appears that hadn't been thought of in the design. So something like, can a robot detect and avoid a glass wall? Even if all the sensors are working and the motion planning's working, that can be some sort of safety event that causes an issue. So when I talk about safety, I'm thinking about it both from the functional safety side as well as safety of the intended functionality. So with that, we can talk about some characteristics of safe autonomy. The first and the most important just being you need a system that can make real-time intelligent decisions. These decisions are often hard to make because there's a lot of objectives that you're trying to balance as an autonomy stack. And so on top of that, you also frequently have changing environments. You might be deploying in a new factory. You might be deploying a system from a new manufacturer. And so you also have to be highly adaptable when it comes to autonomy. And to have safe autonomy, you also need to comply with any of the relevant regulatory or safety standards that'll typically be driven by customer requirements. And you need to be handling both the functional safety concerns as well as the SOTIF concerns. And so I want to talk about the true cost of developing an entirely safety-critical autonomy stack, kind of like they're doing in the autonomous vehicle space. That's extremely expensive and time-consuming, as we've seen. But not only that, it actually limits your flexibility a lot. Limits the flexibility of using open-source libraries, limits the flexibility in terms of using things like machine learning and AI, which we've shown can have really big impacts on the performance of systems. And so not only does it limit your flexibility in terms of working on the code base, but it's also going to limit the configurability of the software. When you have safety-critical software, that needs to be safety-critical in all the different configurations that a user might use. And so that goes directly against the adaptability objective that we had out of a great, safe, autonomous system. Another thing to think about from a hiring standpoint is just it's really hard to find people who can develop safety-critical autonomy. Trust me, we know. It requires very specific expertise, both in terms of developing autonomy as well as writing safety-critical software. And I think the most important consideration comes when you think about verification and validation. That's something that typically takes 2 to 5 times the amount of time it took to develop something in the first place. And when you're thinking autonomy, you're thinking an adaptable, intelligent system that's going to be updated and having to do extensive verification and validation on the entire stack. It's just not going to typically be worth the time to develop a safety-critical autonomy stack. So the question becomes, what does it look like to kind of separate the burden of safety from the burden of the intelligent decision-making portion of autonomy? That's something people often do nowadays. In fact, a lot of times autonomy is developed by one group. You have safety being considered by another group. There's often friction between those two groups because of these competing objectives I talked about before. So I want to talk about a little bit what an ideal safety system looks like. I think most people think of a force field when they think of some sort of ideal safety system. So it wants to be minimally invasive on the performance, so minimally restrict the performance of the system. And if it needs to take over, it should be minimally invasive when it acts. It should be able to cover as much of the functional safety and SOTIF considerations as possible for the decision-making portion, just to eliminate that burden that I talked about in terms of how difficult and expensive it is to develop safety-critical intelligent software. It needs to synergize with the motion planning stack to prevent issues from competing objectives. Like let's say your autonomy stack wants to go somewhere, your safety system isn't letting you. You need to be able to have communication and synergy with autonomy to prevent things like stoppages and gridlocks. And lastly, it needs to be dynamic, both in terms of being able to handle dynamic environments, as well as being able to actually be dynamic and be safe. And so that's what I'm going to talk about next is, what does it mean to have dynamic safety or safety in motion? If you look at different domains, particularly autonomous vehicles and aerospace, stopping is often not possible or not even a safe thing to do. And even when it is a safe thing to do, it's something that's going to restrict the performance and at the end of the day, the effectiveness of your robotic system. And so a dynamic safety system needs to behave more like autonomy would. So you can imagine this example on the right where you have this unexpected human. It wasn't planned for in the motion planning. A traditional system might slow down the system and e-stop it before it reaches it. But a dynamic safety response might take a minimally invasive correction to move around that human. And so you, of course, need to support dynamic obstacles. And again, this is a concept that's used very frequently in different domains. So I want to give an incredible example of dynamic safety. This is coming out of Waymo, a video they've released publicly. So you basically have a truck coming into oncoming traffic. And the Waymo system, if it had tried to stop here as its emergency response, it would have been catastrophic. And at the speeds they were going, could have resulted in fatalities. And so you can see how quickly this system had to replan, create an evasive maneuver, and execute that evasive maneuver. There was only about a 1.5 second window where it was able to actually see the truck coming into oncoming lane and decide what to do in real time. And so there's a couple key takeaways from this video. One is the very rapid perception of the safety event and how quickly it had to generate that evasive maneuver. And something really important to note is it actually had to violate one of the constraints of the system to do this. One of the constraints for autonomy of these autonomous vehicles is to stay within your lane. But there was a more important constraint to avoid the truck that it had to brake. So that's the type of decision-making that needs to happen for a dynamic safety system. It'll typically involve breaking one constraint in order to, conform to a higher priority constraint. And then I think the most interesting part of this, particularly relating it back to AMRs and warehouses, is the quick return to normal operations. The Waymo didn't pull over to the side of the road and just stop. It seemingly got right back on the road and continued on towards its destination. So even though there was this, large safety event that happened, the system was able to very effectively return to mission and keep moving. So I want to talk a little bit about what such a system would require in terms of the knowledge you need to have. You need to have a good model of the system dynamics You need to know how the system responds to inputs that you give. You need to have a fair bit of information about the environment, as well as different assumptions you're making. And so there's some things you're going to be able to measure, like maybe you can get an instantaneous measurement of where a human is and what their current velocity is, but that might change. The human might start moving, they might start moving new quickly. So you really need to document the assumptions that you're making on potential max speeds, different terrain conditions that could affect braking distance. And lastly, you need to really understand the sensors on your system. So you need to know how quickly it can detect things, you need to know how reliably it can detect things, and you need to know how much uncertainty there is. And there's a lot of uncertainty when it comes to robotic systems, not only from the sensors, but from the localization stack, from the perception stack. The actual dynamics models are always going to be imperfect, especially if it's operating in different environments and as things degrade on the system. And there's also going to be delays in your compute, delays in your signals. And so without having some sort of quantitative framework to bring all these things together, you're just going to do things like inflating safety radiuses and inflating all these things and potentially ending up with a system that's too safe and doesn't let you move quickly and optimize on your performance. So this is the only slide with an equation on it, I promise. But I wanted to give one example framework in a framework that I know very well, which is something I worked on extensively during my PhD, which is a way you can frame dynamic safety in the form of barrier functions. So effectively, this is a way to represent safety as a function. This function is positive when you're safe, and when you go to 0, you become unsafe. So think of that function as something like the distance between a forklift and a human. You really need to understand how that function changes with respect to the commands that you give it and the environment. So you look at that through the time derivative of h, or h dot. And then lastly, you need to actually find a constraint you can give to the system. Like just telling the system, hey, stay safe, isn't an actionable constraint that you can enforce. But one that is an equation like this at the bottom, where you're constraining how quickly that function can go to 0. And you can directly map that function to the inputs being commanded to the robot. So that's the sort of quantifiable framework that we're talking about, and just one example of a type of dynamic safety system. One important thing I wanted to mention in terms of connecting to autonomy, I mentioned it before, but you really need to have a tight integration between a dynamic safety system and kind of the intelligent motion planning, decision-making portion of the autonomy stack. An example of where this works well would be like 2 pilots in a cockpit. They have very clear communication, they have very clear division of responsibilities, they know what needs to be done when different things happen. A bad example might be, imagine 2 steering wheels in a car. I think we all know how that might turn up when the passenger's having a competing objective. There's also some technical concerns that arise. For any controls people in the community, you have to worry about things like integrator windup. The autonomy stack has a different objective than the dynamic safety portion. And so there's a lot to consider in terms of communication with autonomy when you think about dynamic safety. So maybe we can pause for a second here so I can talk about what we're going to show. But this is a dynamic safety system that's implemented on the X62 Vista, which is an F-16. The reason this system exists is because they're testing AI pilots. And it's really hard to verify that an AI pilot isn't going to do something wrong. And so this was a dynamic safety system that 3Laws developed to be able to sit in between the AI and the lower level control system that Lockheed develops to basically enforce different constraints that they want to be able to enforce on the AI that's eventually flying the plane. Here we have a human that's kind of stress testing the different limits. And so this is basically a G-force limit. So the Vista itself already has a safety system. If it detects too many Gs being pulled, it'll do a safety trip, which disengages the pilot's input and basically gives it into the safety pilot. But our system is just going to limit the G-force dynamically as the system operates. It's not going to trigger any sort of safety trip. So if you can continue on in the video, the pilot is basically continuing to pull more and more Gs, and the system's limiting it to the limit that they had in place on the Vista as to not trigger a safety trip. But before we get into the next section, if you pause it again, I just want to mention that this is that connection with autonomy that I'm talking about. The pilot was actually pulling a pretty steady increase in Gs, but as soon as they hit that constraint, there was this natural tendency where the pilot tried to pull more and more very quickly. And so that's the type of thing that also happens with autonomy when it faces a constraint that it's trying to overcome. And one of the things that really has to be considered when you're working with dynamic safety. So if you continue on, I have one more example of a geofence plus an altitude constraint. So they want to be able to constrain the airspace that the aircraft flies in, which includes both boundaries in XY position as well as altitude limits. And so basically the pilot was going, but they're going straight at the geofence while descending in altitude. The plane's going to turn itself. Turning the plane also has a tendency to decrease the altitude, which had the floor engage a little more. But it was very critical to keep the system in motion and keep it on mission, as they say, so that they don't disengage. So I'll talk about some of the key takeaways from this and what we can learn in terms of implementing dynamic safety with autonomy. The biggest thing is the same takeaway as the Waymo video, which is this very quick return to mission, or even not even exiting mission in the first place. A way to handle these safety concerns dynamically and keep the system in motion and moving. A few other things I wanted to share that we learned that was really valuable. One, the pilot needs to be informed of what's happening on it, just like the autonomy needed to be informed. There's a very natural tendency to feel something that they didn't input and try to immediately correct for it. So we had to have a system in place where the pilot would be able to know, hey, we're about to act because of this safety constraint. Something else we learned about dynamic safety is that these interventions need to be gentle at first. If you do a very aggressive maneuver that's very different from what the human's trying to do, then there's even more confusion and even more fighting that's going to result in less ideal cases. And again, just to stress, there really is this natural tendency to fight against constraints. And so that's absolutely something that had to be taken into account for this demonstration. So, to wrap things up and to really bring the point home on AMRs, we can leverage these technologies that are being adopted in autonomous vehicles in aerospace to increase the efficiency and the overall equipment effectiveness of robotic systems. So keeping these systems moving, keeping them productive. Some other advantages of dynamic safety in general is allowing for support for some of the next generation of AMRs, things like mobile manipulators and legged robots that suffer even more from controlled or uncontrolled stops in terms of getting them back into motion. It allows for more human-robot collaboration because you have a much more dynamic relationship between the robot and the human. And then lastly, and arguably most importantly, bringing it back to autonomy, is it really lets you develop and deploy autonomy quicker, the more you can take away safety constraints from autonomy. And so having, an intelligent safety system coordinate intelligently with an autonomy stack allows you to deploy quicker to move across platforms and applications. Again, I'm Andrew from 3 Laws. We have a booth here, so please stop by if you have any questions.
Anyone want to kick us off here? Any questions?
Hi, this is Ramesh. I'm from Ignitarium. We provide the solutions and services for automotive and robotics. So I have a question on the functional safety and SOT if you talked about. I believe this is same as the automotive one, the ISO 26262.
Yep.
So that does not address the safety for AI models and stuff like that. I believe there are new standards coming up. So is there any specific standard that you follow for the AI models here?
Yeah, so the idea here is, it's really hard to develop a safety standard for an AI model. And that's why if you look at this guardrails application on the jet, there is that layer in between the AI and the actual lower level control system. And so the burden of the safety certification becomes on that control portion because it's a deterministic layer that at the end of the day is setting the commands. And the AI is only providing reference signals that it's trying to track. And so a system like this is going to do the AI signal when it can, but it has these formal safety constraints that you can actually verify because rather than being some non-deterministic system that's really hard to do V&V on, you have a deterministic layer that takes that burden off of actually having to certify the AI component. It's in that sense, if you go back to the automotive example, it's like a safety element out of context that you use in between the AI and eliminates a lot of the burden there.
That's interesting. I'll quiz you on that later. Any other questions for Andrew?
Hello, I'm James Burton from Bastion Solutions. So my question is, how would you explain dynamic safety to classical controls engineers or safety engineers who are, maybe they're just going to say, you have to take the worst case scenario and nothing else will work?
And let me add on that just for a sec, because I think there is sort of this fascinating discussion in the safety world between, it had to be deterministic safety and then, the role AI will play going forward here. So this is what I was going to quiz you on, so I might as well do it now.
Yeah, great. Great question. Something we've had to learn a lot is how to talk to the more traditional functional safety people. The reality is, for a lot of these emerging applications of autonomy, you literally can't take into account the worst case and still have an autonomous system. Like autonomous vehicles is a great example of that. If you were to truly take into account the worst case of what other actors could do if they were malicious, there's absolutely nothing you could do. And so that's why concepts like responsibility-sensitive safety come into play, because it's really just, you have to be as good as you can, but you're never going to be able to always account for the worst case. You're going to have extremely conservative systems. And that's why frameworks like this that really let you quantify and do a proper risk assessment and be able to show metrics on this is what I can handle, these are the assumptions that I'm making. We're saying a human's going to move, 5 feet per second in the warehouse. Like, we're not going to have Usain Bolt sprinting around, right? Because if you account for Usain Bolt in your warehouse, your forklifts aren't going to be able to move. And so I think it's just a different thinking in terms of, looking at safe autonomy and what really needs to be done. I know statistical models are really important to the autonomous vehicle community, just running lots and lots of simulation and showing that it's, at least safer than human drivers, because there's a lot of accidents with human drivers. But I think, a quantitative framework is really what needs to exist in order to be able to really make that argument, because up until then, people don't want to hear it was simulated 1 million times and it only crashed twice, right? They want to be able to have something more concrete than that.
All right, Andrew, thank you. Thank you very much. We appreciate it. 3 Laws Robotics.